All right. So last time we were talking about process states, where the book calls processes and jobs basically the same thing, uses those interchangeably. We talked a little bit about kind of what goes into a process. Think of a process as a data structure. Or if we were implementing a process, we'd think of it as an object, a Java object, where we'd have a stack and a heap data structure. We have a section for the data and a section for the text, and so each of these are kind of objects within themselves. But a process is really a data structure. Process state. When a process is originally started, it's new. When it's actually running on the CPU, it's running. When it's waiting for some event to occur, that would be like I/O. That would be as a result of an interrupt. It's waiting. When it's standing in line to get the CPU time, it's ready. And when it finally finishes, it's terminated. Okay, so those are the different process states. And here's a little diagram that shows the same thing. So here is the CPU right here. So we're ready, we get dispatched to the CPU, we might get an I/O or event wait, so an interrupt, go into a waiting state, deal with the I/O, jump back into the line to use the CPU, rinse, lather, repeat. Notice another kind of interrupt here, this top interrupt arc. This is going to happen when we're running on the CPU, and depending on what scheduling algorithm we're using, it's no longer our turn to run on the CPU. So to generically talk about that right now, we'd say that might be time-based. So every process that's running on the computer, well, every process that intends to run on the computer gets a certain number of cycles. Okay, a cycle would be, let's call it one iteration through the CPU, one magic trick on the CPU. They get some number of cycles, or they get some amount of time. These are some options, but basically they don't get to jump onto the CPU, complete their entire task necessarily. They get to use the CPU for some portion of time, then they're interrupted and have to go back into the line. All right, so if they're interrupted, they're still cooking along, they go back and just get into the back of the line. Or they might get interrupted and go into a waiting queue. So by our two examples here, they've either run out of time on the CPU resource, or they've been interrupted due to I/O. There are some other things that could be, that could interrupt them as well, but let's just call them. Those two are, most obvious ones. So this is kind of the cycle of life here in the middle. Cycle of life would be the whole thing. It's created. Now it's competing for the CPU, and ultimately it finally finishes. All right. All right, process control block, a PCB. This is a data structure that contains a process. All right, so when we look at this, I want you to keep thinking of these things in terms of data structures. So everybody in here has had 300, or is supposed to have had 300, right? All right, so with 300, well, actually, is that necessarily true? I think you could take this class with just 250. I'm going to assume you've had 300. Whether it's an official prerequisite or not, it doesn't matter for the conversation we're going to talk about here. But in 300, we talk about these concepts of data structures. And so day one of 300, we talk about this concept of a data structure. What is a data structure? If you had to give me a concise definition of a data structure, what would you say? I'm sure Abe would say something like a structure for holding data.
Exactly what I was thinking. You have
This link.
Connection.
This link. Yep, I'm with you. Well, I mean, that's better than the Tim Evan multi-threading example.
Yeah. But we don't use the Tim Evan multi-threading.
Forbidden fruit. That's recorded. Yeah. Funny thing is, I actually think my pastor watches these videos. He's interested, huh?
Really?
Yeah, I think he's interested in some of the stuff, and Obviously, I'm the greatest teacher in the world, so every class you learn some stuff, and it's like a Jim Gaffigan comedy. Probably funnier than Jim Gaffigan. He's like hit and miss. He only has a couple of skits that are hilarious. The rest of them are kind of, he just does everything with the voice. Like, Hot Pocket. All right. So everybody got it that time. You might not have known his name was Jim Gaffigan. Well, so data structure is a structure for holding data. I want to think about these things as an object that organizes data in some way. For people who've already had 300, when we hear the term data structure, we immediately start thinking about linked lists, stacks, queues, trees, things like that. Well, these are organizational theory-based data structures that kind of exist globally within computer science. But there really is a limitless number of data structures. For every single thing that exists, we might need a structure for organizing it. If you have a bunch of shoes at your house, you go out and you might buy a shoe bench, which organizes shoes. You might get one of those things that hangs over the door that you stick the shoes in. That's another organizer. You might just have a pile in the closet. That would be the pile data structure, right? I use that one often. Actually, I don't put it in the closet. My pile data structure is on the dining room table, the chair. That's where I keep all my clothes. And then the cat's pulling on the floor, and then I get yelled at. But in any case, these are all data structures. So I don't want you to limit your idea of a data structure to linked lists and stacks and queues and arrays. So a PCB would be a data structure. It's a specific thing for holding process stuff related to a process. Okay, so if we look at the PCB, we see that we're keeping track of process state, the program counter, the CPU registers, CPU scheduling information, whatever that is, memory management information, whatever that is, accounting information, whatever that is, and I/O status information. So these last four are kind of just like these catch-alls, right? Those are probably data structures within themselves. CPU scheduling information is probably a collection of stuff, probably its own data structure. Collection of stuff, collection of stuff, collection of stuff. Process state. Well, we've seen the different states. We can have new, ready, running, waiting, terminated. Those are our various process states. How do you think those are implemented in a computer? Think they're implemented as strings? So if I was writing, let's jump into Eclipse here. I'm going to create a new class. We're going to call this guy PCB. So we're going to create a PCB data structure. So there's PCB. We're going to paint by number here. And we're going to have process state being one of the dudes that a PCB holds on to. Well, since we look at process state as human beings, and we see that we can have new, ready, waiting, running, terminated, those all look like strings to us, right? So we would probably say something like string process, or let's just call it, oh, I want to name it the whole thing, process state, just for clarity. 3 S's in a row. All right, so we might say this guy is a string process state. And when a PCB is originally created, so let's do our constructor, we might set this dot process state equal to new. Was just created, right? Okay, well now we have an issue though. We're storing these things as strings because human beings like strings. How much memory does that take up? What's the minimum amount of memory the string new takes up? Well, a string is a collection of chars, correct? How big is a char in Java? What do you think, Evan? You're not even paying attention, are you? Are you lying? Alex, what's on the screen? Video games? Google? You know, Tim? How big's a char? A byte? Oh, maybe you're right. Why do you immediately think you're wrong? When did you learn about the size of these different primitive types? 200 probably. And then again in 250. Shouldn't it be ingrained in your soul by now? What if somebody walks up to you on the street and asks you how big a char is?
For money.
Yeah, it could be cash cab. What if you get in cash cab in New York, you're visiting New York or Idaho, wherever the heck is you? Do you have cash cab Idaho? That'd be like one of those hay balers that would. And what if they ask you, in the Java programming language, how big is the char primitive type? I heard you make a guess there, Abe. What'd you say?
I did.
I heard something. Oh, was it Alex?
He made a guess. I'm pretty
Oh,
sure.
did you? What'd you say? 2 bytes? Is that a guess or an answer? Answer. It is 2 bytes, 16-bit. Why is it 16-bit? Evan? So 16-bit, 0 to 65,535. Those are the number of unique characters in the Unicode character set, right? So we need 16 bits to control that. So if we have 2 bytes, 2-byte, a byte is 8 bits, Evan, by the way. So you had that one? Okay, I had that one. All right, so each of these is 2 bytes. We have 3 of them. So we have 6 bytes of data that this is taking up, correct? Okay, 6 bytes of data, 18 bits. How many bits is it? 24 bits, right? But you guys are just killing me. Can't even pay attention that long. It's like all right. So we have 24 bits of data to hold this one string. Now, realistically, in Java, strings have to be written abstractly. So they're probably built to be significantly flexible, right? So realistically, let's just say this is 32 bits of data to hold this state. If you were implementing this at the operating system level, knowing that we need to store this stuff in hardware somewhere, you'd probably want to make it as the smallest footprint possible, right? Is the code related to our operating system something that many people are going to be viewing? No. So how would you implement the state of a process? A number. Okay, what kind of number? What are our options? Byte, short, int, long? Byte. Bytes hold negative 120. This is negative 127 to positive 128. All right, so that'll hold our 5 different states. No problem. All right, so what we might do from an abstraction perspective is we might create another class. Called process state. And inside process state, we might have a bunch of static fields. So we may have static byte new is equal to 0. Static, oh, we can't use new. Yeah, let's call it state new. New state. Static byte ready state is equal to 1. Static byte running state is equal to 2. Static byte waiting state is equal to 3. Static byte terminated state is equal to 4. Something along those lines? All right. So we have a class called process state that has a bunch of static fields in it. All right. So I want to set my process state, which is going to be a byte for this PCB, equal to the new process state. How would I do that? Here's the process state class. How do I get the new process state? How would I call it? Class field or instance field? Class field. How do you know? Static. How do you call class fields? Use the name of the class in which the field was defined. So, if I want to set process state equal to new state, how would I call it? Process state dot new state. So we've abstracted now inside of our own class so that if at any point in the future we decide to change up our numbering scheme, we don't have to change our code here. Does that make sense? And also, this reads nice. That makes sense to us. If I had hard-coded a 0, would it? Right now, we remember that the state new is a 0. But what if we fast forward 6 months? We might not remember our little numbering scheme, correct? Because if you're going to hard-code a 0 here, that probably means that this guy no longer exists. The old way of doing this is you could probably put a little comment block up here listing the different states as a reminder. But from a modern programming perspective, process state.newState makes more sense. That makes sense? So when a PCB first comes into existence, it's going to be set to the new state. Okay, we also have a program counter. Now, program counter, well, remind me, what is a program counter? What do we need it for? Talked about it last class.
Keep track of the programs that are running.
Track of the programs that are running. Remember, this is inside of PCB, which is a data structure for holding a single program, single process. So what's the program counter? Well, what's a process? Process is a running program, or program in memory, right? We've launched it off the hard drive, now it's in memory. When we write software, we write programs, right? We write little ones, little baby mini programs, but we write programs. When you write a program, what do you write it with? Probably Java for most of us. Lines of code. When we compile it, what does that turn into? More lines of code, right? Because we're writing it in a high-level language, and it's going to compile it into a low-level language. High-level languages have a one-to-many relationship with the CPU. Low-level languages have a one-to-one relationship with the CPU in terms of magic tricks. Okay, so we're going to have our, oh man, it's looking bad, isn't it?
It looks a little better than it did.
Actually, it does. It's starting to clear up. It's awesome. I got it in my peripheral vision. So, in any case, when we compile our Java program, it's going to turn into a whole bunch of individual instructions that relate to exactly one magic trick on the software-based CPU the Java virtual machine has. But we could just think of it as our CPU in our computer for our example here. Okay, so we have a big collection of assembly language instructions associated with a process? Well, program counter keeps track of which of those instructions we're on next. Why do we need that? Can't we just start at the beginning and go through? Why do we need to keep track of which instruction comes next? Here, I'll give you a hint. It's a picture hint. Abe?
You're waiting for a process. If it was interrupted and you had to go back and get a input from the user, you don't. When you get back in line, you don't want to have to start at the beginning and then go back to get that same input. So
Yeah, and even beyond that, we're still only getting a certain amount of time on the CPU. So, we're probably not going to, I would say very, very, very rarely does a process completely finish its execution one trip through the line. It would have to be a really small program. Hello World probably does. Actually, Hello World definitely doesn't. Because Hello World, even though it's such a very short program, it's going to enter the CPU, the Java program is, it's going to start running, and then it's going to be interrupted for I/O to display Hello World to the screen. Then it's going to get back in line and run to the end of the program, which nothing else happens after that, but it's still concluding the program. Then it'll move to a terminated state. So even Hello World doesn't finish on one trip to the CPU. It interrupts itself because of the I/O. And we've seen that before, right? When we've written programs that print a lot of stuff to the screen, they take a long time because we're continually interrupting the CPU. Just to show that again here real quick, in case you've never seen that before. To see this in action. All right, so I have a program here. We're going to create an integer called sum. Actually, we should probably just call it count. Doesn't really matter what you call it. Don't even verbalize that. Ay, people. Okay, so we're going to have count. That's true. We're going to go, is this 1,000,000? I just pushed random zeros. 10 million? Oh, good enough. All right, so we're going to go through, we're just going to add each time through here and print it once. So we have one built-in I/O interrupt in this code. Our own I/O interrupt, because we're going to do printing. Okay, so we interrupt ourselves because we need the I/O system to display something to the screen. In here, this is just math code. This is CPU working, CPU working, CPU working. Now, depending on how long it works, we might do this on one trip through the CPU, might do it on a couple of trips through the CPU, but we expect this to run fast. There's our answer. We counted that number of times through. Now, if instead we displayed count each time in there, now 10 million times we are interrupting ourselves. So we are getting in line, we're getting access to the CPU, we're then saying, oh, I need to print something. So we're doing a little math, we're adding one to count. So we're using the CPU a little bit, and then we're immediately interrupting ourselves to display something to the screen. So that same program that just ran instantly is now going to not run instantly. Does that make sense? Because we had to continually interrupt. We took ourselves out of line and moved into a waiting state. This is going to run for a while. Can that make sense? So when you have programs that do a lot of I/O like this, they're going to slow way down. And they slow way down because we move from a running to a waiting state often. And we look at this as just a little quick little jump down here, but actually moving from a running state to a waiting state is expensive. So remember, we got to this discussion when we were dealing with why do we have a program counter. And Abe told us that, well, whenever we leave the CPU for whatever reason, whether it's an I/O request or it's no longer our turn, and we have to go get back in line, we have to remember where we left off. Right? You got to remember that stuff. Well, what else do we need to remember? Oh, we have this thing called CPU registers. We have to remember the current state of all the hardware-based variables on the CPU so that we can reload them into the CPU when it's our turn again. So initially, they're all going to be our initial values, and then we're going to fill them with new stuff as we start running through our assembly language instructions. But when it's no longer our turn on the CPU, we go through something called a context switch. So when we move from a running state to either a ready state or a waiting state, which then leads to a ready state, when we leave the CPU, we have to do a context switch, which means we need to store all the current information related to ourselves in our PCB data structure. Which line of code did we leave off on? Program counter. What's the current state of all the hardware variables? Those are the registers. And a bunch of other crap. Okay? That gets loaded into our PCB data structure as we leave the CPU. Why? Because eventually we're going to get back, well, not necessarily eventually. If we are waiting for user input and they never enter it, we're just going to stay in a waiting state forever. But hopefully, eventually we get back into line for the CPU. And when we go back onto the CPU, there'll be another context switch. There'll be a process leaving the CPU that will load stuff into its PCB, and then there'll be a process entering the CPU that'll load stuff onto the CPU from its PCB. That make sense? That's expensive. And that's actually an important aspect of operating system design when we talk about process management, is what's that sweet spot? How do we come up with the right amount of time and the right number of cycles that we're going to give a process on the CPU such that we get maximum efficiency, or at least a high level of efficiency, without wasting tons of time context switching? What if we gave every program one CPU cycle? We let it execute one instruction. We'd spend most of our time storing the crap that was on the CPU, moving into another ready state. We'd spend every single time something leaves, we have two context switches. One for the process leaving, one for the process entering the CPU. That's expensive. That takes time. So we need to minimize the number of context switches while maximizing user experience. Because remember, the end user expects all this crap to keep happening all at the same time. If we're one user and we have 5 programs running at once, we want all 5 programs to feel like they are all running at the same time. True? And that's only on a single user computer. That's the easier problem to solve. What if we're on a multi-user operating system, like a Unix, where we might have 200 users using the system at the same time? They're all running their VI word processor, and they all expect it to be running in real time for them. 200 different programs. Well, for that, you'd think we want to give program 1 some time, give program 2 some time, give program 3 some time, give program 4 some time. Really leverage this idea that CPUs are very fast. We keep looping it back around, looping it back around, looping it back around. But we have to give it enough time on the CPU that we don't spend all our time context switching. So you kind of see this battle as an operating system designer, this battle we have to go through of kind of finding that right place. And understanding, this kind of goes with the last question on the exam, or one of the last questions on the midterm, that dealt with how do different operating systems deal with stuff depending on what their goals are, who you're trying to make happy. You make decisions that are different depending on the goal of the operating system. So it's really an important thing, and it's something that when they release updates to operating systems, or even if we look at the evolution of operating systems, we deal with this idea of how often do we context switch? We lucked out in our early operating systems. Before multitasking, when we had single programmed operating systems, like DOS, for example, we didn't have to worry about context switching. You launch text editor? Cool. let me know when you exit the program, and then it will leave the CPU. And that's only a half truth because the operating system behind the scenes had to kind of stay in memory and it got some CPU time. But really, we just had to alternate between two processes. And we could give the end user most of the time on the CPU and just interject when we had to. Because back then, operating systems were, for its time, they were complex. But compared to today, most of us would not be overly impressed with DOS in terms of its capabilities by today's standards. In its time, it was amazing. Okay? So, kind of an interesting thing. Think about how much money DOS made when, by today's standards, it was a fairly simple program. Okay, so though that kind of gets us into this idea that we need to play around with these variables to figure out what's that sweet spot, and that might be different for every operating system. It might also be different when we deal with modern operating systems. Modern operating systems have some artificial intelligence in them which try to figure out how you commonly use your computer. If you're somebody who's constantly switching between applications, it might choose to context switch more often to make it feel like those applications are all getting real-time support. If you're somebody who stays in one application for prolonged periods of time, or even certain applications, when you're in Microsoft Word, you tend to use Microsoft Word for a prolonged period of time, it might give that guy a higher priority. So that particular application might get more CPU time. So we can see how this might evolve over time. That really follows the evolution of operating systems. All right, so process state we're probably going to store as a number, and we're going to store it as the smallest number we can possibly store. Now, so as a computer science trivia question, what is the smallest number of bits that we can store process state in? Technically. Java, we can't do anything smaller than a byte. But what's the smallest number of bits we can store process state in? Go ahead. 3 bits? Why 3?
Because that's how many you need to get up to 5.
To count to 4 for 5 different things, 0 to 4, we need 3 bits, right? So a 4 would be a 1, 0, 0. A 3 would be a 0, 1, 1, so on and so forth. So we only need 3 bits to represent our process state because we only have 5 states. But it just so happens Java, and actually all high-level programming languages, I can't think of one that allows us to have something smaller than a byte. Is that true? Does C allow us to have a nibble? C might allow us to have a nibble. I don't think so. I don't think it does. I'm about 84% certain it does not. But generally speaking, our modern high-level programming languages, the smallest integer type we can store is a byte. The reason I mentioned C is because C was originally designed as a language for writing operating systems. And because of an efficiency perspective, and because this is really something we deal with pretty often. Having codes associated with states or codes associated with values. Now what's kind of interesting is when you see web errors. So you've ever seen like a server error 400 or server error 500 on a web page. Those are error codes. Do you think there's 500 different error codes for a web server? Probably unlikely, so it just surprises me that they use numbers that big instead of error code 3. Maybe error code 500 seems more serious. It shows up as a bigger banner. Okay, but in any case, we only need 3 bits to store this, but we're going to waste a little space and use 8 bits. As opposed to making these ints and using 32 bits, which would waste a lot of space. Okay, so we're only wasting 5 bits here. And actually, in reality, we're only wasting 4 bits, because I don't think, it doesn't. Java doesn't support unsigned values. C does. So an older language like C will allow us to create a primitive type that is unsigned, which will then use all of the bits for value. So an unsigned byte would be 0 to 255. Signed byte is negative 127 to positive 128. So we definitely don't need negatives, but whatever. We're just wasting a little bit of memory here, but not the end of the world. All right, but the punchline there is computers like numbers, not strings. The strings actually become a somewhat of a nightmare because we're mapping things constantly. A char in and of it, a string is a collection of chars, and a char is a mapping from a int to a character, and a character to an int, using the Unicode table, or in C it would be the ASCII table, which only has 256 unique characters on it. So in any case, mapping for strings is expensive. We have to go through 3 steps to get a value out of a string. All right, so process state we're doing as a number. Program counter, probably also a number. What kind of number for our program counter? Remember, program counter keeps track of where we currently are in the program, which line number we're on. What kind of value do we use for a program counter? Is it a byte? Is it a short?
Wouldn't it have to be unlimited value?
That would be ideal if it was an unlimited value. Unfortunately, they don't sell unlimited size registers for our computers, so it's problematic. Is kind of what I'm getting at there. But ideally, an unlimited value will allow us to have programs of any length. So we actually just introduced a new limitation. We never think about this. What if our program is too long? Kind of becomes interesting, doesn't it? Now we can probably say, let's say we use a long. Okay, 64-bit number. And even in Java, which is signed, that's 2 to the 63rd power, which is this gigantic number. So what's that? 1, 2, 3, 7, 8. So another 9 zeros after that. So 922, giant number, right? Really big number. If I had it written out, I could actually tell you what the number is. It's probably some quintillion or quadrillion or something like that. Big, big, big number. So technically, if we use the 64-bit register to store our program counter, because even though we're writing the software for this, underneath the hood, it's going to have to store that somewhere, right? And when we're dealing with program counters on the CPU, we want it to be stored fast. So we're probably not putting this out to system RAM. We're probably throwing it in a register. Or in a worst case, one of the caches. But for this, it would be in the register. We want to keep this as close to the CPU and as fast as possible. All right, so maybe we use a 64-bit register, which, mind you, is only relatively recent. Only our modern processors that are 64-bit processors have had 64-bit registers. Before that, we had 32-bit registers. Before that, we had 16-bit registers. Before that, we had 8-bit registers. And in the really, really, really early computer processors, prior to general purpose computers, we had 1-bit processors, just to prove that we can store a bit of information. Okay, so we're going to use one of our registers, let's say it's a 64-bit register, to store our program counter, and we need to be able to store, let's just call this 9 quadrillion. So we can have a program up to 9 quadrillion lines of code. Is it quintillion? Oh, wait, whatever. Huge number. Huge number is good enough for this example. Not an infinite number, though. Just a huge number. Go ahead.
Would it like crash or give you an error, or would it start at the 9 quadrillion line if you had more lines than that?
Well, here, I can show that in code. We'll do this with a byte. So this is going to start B off at 0, and forever it's going to print out B and add 1 to B. So this is going to go 0, 1, 2, 3, all the way up to 127. Then it's going to circle back around to negative 128. Is that right? Yeah. So that's working. So because of how math works, what you end up having is once you hit 127, you add 1 to that. It ends up circling back around and you lose the carry bit. And it becomes the negative number. So we can't have that. We can't hit line 9 quintillion and then all of a sudden just say, oh, next line is 0. Go. If we're dealing with an unsigned value. Okay? So that would be problematic. So at this point, if we deal with 64-bit registers, our computer programs are limited to 9 quintillion lines of code. Is that a problem? Probably not is the punchline there. Today. But we go back historically, we say, okay, well, Bill Gates once had a quote, you'll never need more than 32K of RAM. Well, we need a lot more than 32K of RAM today. Most of us have 8 or 16 gigabytes of RAM, or at least 8 gigabytes is probably fairly common. 16 is probably not so common. But in any case, 4 gigabytes is our budget pleaser computers today. A lot more than 32K. So over time, our programs are going to get bigger and bigger and bigger, more complex. Now keep in mind, I'm not saying this is going to be 9 quintillion lines of Java code. Remember, Java is a high-level language with a one-to-many relationship with the CPU. So we can write substantially fewer than 9 quintillion lines of Java code. And upon compilation, when it turns it into a low-level code, which has a one-to-one relationship with the CPU, we could have a lot of lines of code. For instance, the Hello World program. Let me show you this real quick. This should be. So as an example, let me blow it up a little bit. Here is assembly language for Hello World. So this is kind of filler stuff here. Program actually starts right here. All programs begin and end with main, if you will. So we're moving the number of characters that we're going to print into this register, a register called EDX. Then we're moving the actual value we're going to print into another register. Okay, now we're moving, this deals with file stuff, into another register. This deals with the system call that's going to actually display it, the guy that knows how to display something to the screen, into another register. This is our call to the kernel to execute that system call. Then we'll actually move it, move the system call number for the exit status, saying we're done with this I/O. Call the kernel on that guy. So this is one system call. This is a second system call. Okay, and notice down here, this section is our data. This is the hello world that we're printing. And this is its length. So these are two variables being defined. And keep in mind, assembly needs to figure out how to store these somehow. So this is even higher level language than machine language. Okay, remember when we talked about there are 3 kinds of languages? We have machine language, we have low level, we have high level. So this is something a human being could have coded. But doesn't this look significantly less friendly than Java? Yeah, we like Java over this. But we can sort of kind of follow this. So our short little hello world program turns into a fairly substantial length program here. And we can certainly move beyond that and understand that programs that actually do something are probably quite lengthy in assembly code. So maybe a 9 quintillion line assembly program isn't quite as absurd as it might seem. It's still, by today's standards, it still is absurd. But our programs every single year are getting more and more complex, right? So eventually, what do we need to do? Well, we'll have to have 128-bit processors. Nobody's talking about those yet, right? 20 years ago, they didn't talk about 64-bit processors. Everybody was still excited about 32-bit. Even by from a video game history, it's kind of has the grunge appeal today. 8-bit graphics, right? So the old 8-bit video games like Nintendo stuff. Then we had our 16-bit systems, Super Nintendo, Sega Genesis, 16 bits of power. But all our machines today are 64 bits, right? Xbox One, PS4, 64-bit processors. Huh? Which part? I am? Oh, that's my delivery. That's why this is gold, like Jim Gaffigan style. Who gets as excited as I do about computer science? Evan, maybe? Close?
Sorry, I was trying to give
All right. I'll see everybody on Friday.